So in this course on rheology, we've been looking at material response in terms of different classifications. We've looked at viscous, viscoelastic, linear viscoelastic and nonlinear viscoelastic response. And in these segments of lectures, we are looking at some rheometer demonstrations. In the previous segments, we looked at steady shear and oscillatory shear. We looked at a system where there is a transition so that rheological properties change as a function of temperature. We also looked at how stress growth happens in a material, and we also looked at the steady shear data. Now in this segment, we will look at another important measurement which is required as a measure of viscoelasticity, which is normal stress difference. And so most of the commercial rheometers are equipped in terms of measuring the first normal stress difference. The second normal stress difference is far more difficult to measure because the measurements of pressure on the bottom plate have to be done. The radial, how the pressure varies as a function of radius, has to be done. But as we will see, first normal stress difference is easier to measure. And so we will look at a demonstration of how first normal stress difference varies for an example material. And quite often, of course, we have tried to correlate the rheological response with the microstructure of the material. So it becomes important to examine the material while it's being sheared. So we will take a look at example material where we can actually look at the structure as it is being sheared. So with me we have Shruti and Jacob, who are both PhD students in our group. And as I mentioned last time, there are several different rheometers which can do all these rheological measurements, and they all will have strengths and weaknesses. We are doing the demonstration with the instruments which are available in our lab. So we will first start by looking at how is normal stress difference measurement done, and Jacob will demonstrate it.
Okay, so we know that when a Newtonian fluid is subjected to simple shear, the normal stress difference is 0, and therefore for a Newtonian fluid, the net force exerted in the direction normal to the direction of shear is not there. For a non-Newtonian fluid, the normal stresses that are developed are not negligible. Sometimes their magnitude is so high. For example, a rod climbing fluid, a non-Newtonian fluid which climbs the rod which is used to shear it, the the fluid overcomes the centrifugal force that is exerted on the fluid, and therefore the normal stress that is developed there in the RR direction is very high in magnitude. So normal stress that is exerted in case of a non-Newtonian fluid is therefore not negligible. Therefore, it is important to also look at the normal stress data of a fluid when it is subjected to simple shear. So how does rheometer measure the normal stress? So in the earlier video, you saw that the rheometer has a motor which is using which we can measure the torque that is required for shear, but it also has a normal force sensor, which is a piezoelectric transducer. This same sensor is used to detect the 0th position of the geometry. You saw that when the geometry was brought down to the bottom plate, when the geometry touches the bottom plate, the normal force shoots up, and hence the 0th position is detected. And therefore the same normal force which is transducer which is used for that purpose can also be used to measure the normal stress that is developed during the course of shear flow. Today we are going to look at the normal stress data for two different types of fluids. One is Newtonian fluid. I have with me two different Newtonian fluids. One is of viscosity of 100 cp, 100 centipoise. Both are silicon oil. Another one is of 1000 cp. I also have with me gel which is made up of biopolymer called pectin. Pectin is a polymer that is present in the cell walls of plants. This polymer is widely used in the food industry. This as an ingredient in jams and fruit juices as due to its stabilizing property, thickening properties, etc. So this particular fluid during its processing stages often undergoes shear flow, and therefore this fluid, being a viscoelastic fluid, will experience normal stresses which are not negligible. So in our test today, we will look at the normal stress data or normal stress that is developed during the shear flow of this fluid. So what we are going to do is apply a steady shear flow, which we saw in the earlier demo. So we are going to increase the shear rate from a low value to high value and look at the shear stress developed as well as the normal stress that is developed. So in this rheometer, whenever a thrust is exerted onto the top geometry, the force that is detected is positive, which means whenever a sample expands or pushes the top geometry, the force that is developed is positive value, and whenever the sample shrinks or pulls the geometry towards the bottom plate, the value is negative. Hence we can understand what happens during the shear flow, whether the sample shrinks or dilates during the course of shear.
When Jacob is saying shrinking or dilation, we should remember that these are incompressible fluids, so the effect is apparent effect. So the fact that it appears that the sample is pushing upward, it appears as if it's expanding, or when the sample is pulling over the top geometry lower, then it appears as if it's contracting. But in general, there is no expansion contraction in the material because it's an incompressible fluid. The other thing I just wanted to point out was also the fact that silicon oils, as were shown, are extremely important for the overall rheological measurements. Whenever we do a new material, whenever we do a new type of test, these standard fluids are very crucial for us to do sanity checks. Basically, to make sure that we get the results that we expect from the standard fluids, ensure that the working of the instrument is according to what we expect. And that's why in this case also, we are going to show you not only the results of a pectin gel, but also the standard fluids such as silicon oil, which is supposed to be a Newtonian fluid.
I am going to use a cone and plate geometry for the purpose. This is a cone part with 50 mm dia with a cone angle of 1.99 degrees. The initialization of the rheometer as well as the motor adjustment process were all done prior to attaching the geometry. After the geometry is attached, the geometry is detected and zero gap is set, like it was demonstrated in the last video. Once the zero gap is set, the geometry is lifted to position where the sample can be loaded easily. Now I am going to load the sample onto the lower plate of the rheometer and bring down the geometry to the measuring position. After the geometry is lowered, the excess sample is trimmed out using a spatula. This graph that that's shown here shows viscosity on the y-axis and shear rate on the x-axis. On the second y-axis, there is this first normal stress difference, and the test has started now.
One of the important factors to remember while acquiring rheological data is the amount of time that is given to the instrument to collect one particular data point. For example, when we are doing measurements at very low strain rates, it will take some time for the instrument to come to steady state, and so therefore long time may be required. and that's why here you see that the first data points have appeared, but the next set of data points will take significant amount of time. But when we go to higher strain rates, we expect the steady state to be reached faster. And so the measurement point duration for each and every measurement, how much time is required, is a very crucial decision that a rheologist has to make while doing the rheological characterization. So you can see that the first 3 data points have been measured, and the circles are the viscosity. The diamonds, which are the normal stress difference, is also there, but you should notice that the axis, the magnitudes are different. First of all, the normal stress difference is negative, and at least in this small range, it does seem to be decreasing quite strongly. But what we will do now is to cut and show you the final data, so that we can get an overall idea of how is viscosity and normal stress difference for these samples.
Now that we have completed the test for all 3 different samples, we can see here the results of viscosity as a function of shear rate for the 3 different samples that I showed you earlier. The silicon oil samples shown in black as well as red show a constant value of viscosity as a function of shear rate, whereas the pectin gel shows a strongly shear thinning nature, which is expected.
One thing to notice is also how the low viscosity sample, there is at low strain rate, there seems to be the viscosity value not being so constant, and that's again expected, because at very low strain rates the torques required are extremely low, and sometimes we may be in the instrument limit. So therefore, whenever we make measurements at low strain rates, we should always be careful.
If we look at the first normal stress difference data for the 3 different samples, which is shown here, you can see that the Newtonian samples do not show a significant value, or it's almost 0 value of first normal stress difference, which is quite expected for a Newtonian fluid, but the gel shows a large value of first normal stress difference, which is also negative. To give a comparison, the red curves show the first normal stress difference both in the same axis. The value of normal stress that is developed in this case, for this material, when you shear it, is very high compared to the shear stress. So as I mentioned earlier, the normal stress that is developed in such materials cannot be neglected, because their value is much high compared to the shear stress itself. So the normal stress has a great contribution to the deformation behavior in this material.
Just to remind again, this is magnitude of the normal stress, as we had seen on the previous slide. In fact, it's negative normal stress. So just to compare, since we want to compare both shear and normal stresses, they are plotted on the same graph. So we have taken just the normal stress magnitude itself. The other thing to notice in this data is the fact that again at low strains and high strains, there seem to be some fluctuations in the normal stress. So one needs to be careful about analyzing the data at such extreme conditions. The other interesting thing about this particular sample is the normal stress difference is almost independent of shear rate. This is not normally the case for a lot of viscoelastic materials like polymer melts, where normal stress difference is actually a strong function of strain rate itself. So again, depending on the material and its microstructure, we would have different types of dependencies of normal stress difference on the strain rate. So in this example, we saw how normal stress difference is measured, and when we do the steady shear measurements, we can do both the shear stress measurement, which is based on the torque measurement, and the normal stress measurement, which is based on the thrust measurement. And in this particular example, we saw that the sample generates a negative first normal stress difference, and this is in fact one of the unique materials which gives a negative normal stress difference. From now, what we will see is in case we need to examine the material microstructure along with its rheology, what kind of a tool we can use, and specifically we will look at doing microscopy along with shearing.
So there are many additional attachments available with Rheometer to have some additional information about the material as we do the rheology of it, like if it is a steady shear or if it is an oscillatory shear. Like in all these cases, what is really happening to the material we don't know. So if you use a additional attachment like microscope, with this we can find what is really happening to the material when we shear it. So there are different attachments available with the rheometer, like rheosals, that is small angle light scattering, and Raman microscope, that is a spectrometer attached with rheometer, and the other one is rheomicroscopy, that is a simple microscope that is attached with the rheometer. So that is what we are going to demonstrate here, that is a simple microscope attached with rheometer. In case of emulsions, where the droplet sizes or the particle sizes that are big enough to be captured with a simple microscope, we can go for rheomicroscopy. So here for this demonstration, we are going to use an emulsion, that is an oil in water emulsion, that is decane in water, that is stabilized by a particle, that is silica. So they are called Pickering emulsions. So as we all know, emulsions have wide applications in various fields like food industries, pharmaceuticals. There are many applications for emulsions. So there is in all these applications, the emulsions will be undergoing some kind of shearing happening to that. So we should be knowing like what is going to happen to the emulsion, if it is going to be stable throughout, if it is going to break, if the droplets are going to remain as such throughout. So all these things we should be knowing before making a product. This is the material that we are going to use today. This is silica stabilized decane in water emulsion. You can see the droplets on the walls of this vials. On the microscope we can see it more clearly. These are micron size droplets, around 50 to 100 microns in size. Before starting the rheomicroscopy, what we should know about the rheometer is that we have already told that there are different kinds of peltier that is available for the rheometer. So here what we have is a glass peltier. So it is having a glass bottom plate under which we can attach a microscope. There is a microscope attached in the bottom of this. So this is a stand, and inside there is a microscope attached. So it has a camera attached to that. So there is a camera on top of which there is an objective lens of the microscope which focuses on this sample, and whatever it captures will be projected on the screen. So let us now load the sample and do a steady shear test like this. Now let us load this emulsion sample and let us see what will happen to the sample as it is getting sheared. So for rheomicroscopy, we should need a glass peltier, and also we should need a glass geometry. So the geometries which you have seen before are not transparent. Now this is a glass geometry through which we can focus onto the material and see what is happening to it. So this is a PP43 glass geometry, that is parallel plate 43 mm dia glass geometry. So this is what we are going to use for this test. Here also, after attaching this glass peltier and attaching this geometry, we have to initialize the rheometer, we have to do all the calibrations, that is inertia adjustments, motor adjustments, everything we have to do, then only we should start the test. So here I have already done all these adjustments and I am going to start the test. The set zero gap is done. Now it is going to its lift position where we can load the sample. Now I am going to load this emulsion sample onto this.
One of the important things in many of these samples is to make sure that the sample that you are withdrawing is actually representing the sample that you want to measure. Many times in samples such as dispersions, emulsions, basically multi-phase systems, it's possible that there is a small amount of settling or small amount of creaming that happens. So before you do the measurement, it's essential for you to homogenize the sample so that you know what you are measuring, because otherwise you may be withdrawing a part of the sample and it's not really representative of the overall material that you are trying to characterize. So in this case also, what you can see is this sample is fairly homogeneous throughout. Given that it's an emulsion, it is entirely possible that at the top there may be a small cream layer, or given that it's oil in water, there may be a small clear water layer below. So in this sample you don't see such heterogeneities, but if such heterogeneities are there, you need to worry about what are the measurements, what part of the sample you are measuring, and what do your measurements mean.
Okay, now I have loaded the sample onto this glass peltier. Now I will bring down the geometry to its measuring position. So here also we have to do the trimming of the sample after loading it, but here we should be a little more careful because we are using a glass peltier, so we should not give any scratch or leave any marks on that. So be careful while handling glass peltier and glass geometries. Now I have loaded the sample, and this is how the sample looks like when we look it through a microscope. And this is the image that the microscope attached to this rheometer is capturing right now, and this is how the sample looks like before starting the test. Now you should notice how the drops looks like before starting the test. These dark black colored ones are the droplets of oil which is stabilized by silica, and this is the continuous phase. Now I am going to start the test. So this is a steady shear test. So here I will share both the screens to see what is simultaneously happening to the rheology of the material as well as its microstructure when it is getting sheared. Now I will start the test. So I am going to do a steady shear test on this with a shear rate ranging from 0.1 to 1000 second inverse with a pre-shear of 0.1. Okay. Let us start the test now. Now we can simultaneously observe what is happening to its viscosity and what is happening to the material, its microstructure as it is getting sheared. If you look carefully, we can see that it is moving slightly, like very slowly it is moving, the droplets are moving very slowly because now the shear rate is only 0.1 second inverse, but when it reaches a higher shear rate, we can clearly see that how the droplet is moving in that continuous phase. Okay, so now the test has started. The shearing is happening in this direction, like in an anti-clockwise direction. If you if you carefully observe, you can see that the droplets are moving in this direction. So this is the variation in viscosity as a function of shear rate that we are observing now. Even at such small shear rates, we can see that the sample is showing a shear thinning behavior. Yeah, it has reached almost 0.3 second inverse, and we can see that some of the droplets have started coalescing and forming bigger droplets here.
One more important thing you can notice is some drops are in focus because they are touching the bottom plate, but there are other drops also, for example here, which are maybe in the other plane. Of course, in this case, this gives us an idea of the layer of the fluid which is right next to the bottom plate, and hopefully whatever we are seeing is representative of what's happening to the rest of the drops, because this is a uniform shear. If you recall, this is a simple shear. It's a constant velocity gradient, so constant strain rate that is being applied, and so hopefully whatever you are measuring in terms of the droplet sizes at the bottom plate are representative of what's happening throughout the sample. Another important thing to notice is in this parallel plate flow, the direction is in the theta direction. So you can see also how all the droplets are moving nicely in theta direction. So therefore, the assumption of one dimensional flow seems to be quite reasonably valid. all the droplets, if this droplet is there, it's just moving only in theta direction. Droplets are not moving in this or the other direction. Similarly, a droplet which is in focus remains in focus, which means the z direction motion is also not there.
Okay, now the shear rate has reached almost 2 second inverse. So now we can clearly see that many of the droplets have coalesced and formed very large droplets in this, and also the droplets are moving very fast, and actually the frame rate of this microscope camera which we are using is just 30 fps. So after a shear rate of like 10 second inverse, we may not be able to capture the droplet motion properly, but if you use a camera of a higher fps, you can capture it properly. Now the shear rate has reached almost 100 second inverse, and now the speed is too high for the camera to capture. So if we use a higher fps camera, as I said before, we can capture this motion also. Okay, now the test is completed, and we can see clearly the shear thinning nature of this emulsion and how now the drops are arranged after the test. So we have seen that the droplets were nicely homogeneously arranged before starting the test, and now after the test how it has arranged here we can see. Sorry. Yeah, so here we can see there is a nice arrangement of droplets that has survived the shearing, and we can see the continuous phase has separated out and formed a layer here. We have seen that at low shear rates the droplets were moving only in theta direction. The arrangement after the test shows that it had some kind of secondary flows or flow in R direction to come to the periphery of this geometry. And why this emulsion droplets acquired this particular arrangement has to be actually further investigated. This is the summary of the test which we have carried out. You can see that before starting the test, the droplets were nicely arranged, like nicely and homogeneously arranged like this, and after the test we can see how it is arranged. Like this, droplets which have survived has arranged along the periphery of it, and the continuous phase has separated out. So when we shear this particular emulsion to a shear rate as high as 1000 second inverse, this is what is happening to it, and in between how this coalescence happens and how it is getting separated out, at what shear rate this happens, and all are captured, and it is given inside this box along with this graph. So this is one kind of test that we can do in rheomicroscopy. There are several other sets of experiments we can do where we can focus on the whole area of the geometry and capture some kind of patterns which they are forming.